Hello, and welcome to my presentation. In this presentation, I will be explaining this paper entitled Iodine Oxidative Addition to Isomeric Platinum II Phosphine Complexes, written by Annette Yahav, Israel Goldberg, and Arkady Vigolok. Let's first consider why this research is relevant. Oxidative addition reactions are an important step in many catalytic reactions, and one example of this is methanol carbonylation. As you can see in the figure, a rhodium complex undergoes an oxidative addition reaction between complex 1A and 2A, and this is followed by a migratory insertion, a CO ligand insertion, and finally reductive elimination to turn a molecule of methanol into a molecule of acetic acid. In other work, SN2 style reactions have been observed to form the cis product of the oxidative addition reaction, but not a lot of work has been done on the mechanistic details of this, which is where this paper comes in. Now let's briefly summarize the findings of the paper. The paper explains the formation of this complex, let's call this complex 2, from a cis and trans precursor, which we'll refer to as 1A and 1B, via oxidative addition. Both precursors eventually create the same product, but two different intermediates are produced along the way. The cis isomer 1A forms intermediate 3, while the trans isomer 1B forms intermediate 4. A wide range of NMR spectra were used to distinguish between the precursors, intermediates, and products, which we'll discuss later. Let's first consider the oxidation states of the platinum in these complexes and do some electron counting. The platinum in the precursor molecules has a D8 configuration and thus contributes 8 electrons. Each of the intermediate and product molecules are platinum 4 complexes, meaning they contribute 6 electrons each. Each ligand donates 2 electrons. On 1A and 1B, this leads to 8 overall donated electrons, and on 2, 3, and 4, this leads to 12 overall donated electrons. Therefore, complex 1A and 1B have a final electron count of 16, and complexes 2, 3, and 4 have a final electron count of 18. This helps to display why the final products are more favorable and why the intermediates 3 and 4 are also relatively stable. Now we can discuss the mechanisms involved in the paper. The first one describes the reaction of the cis isomer. We can see it performs an oxidative addition reaction through attacking the iodine. At low temperatures, this reaction proceeds towards the intermediate, where the iodine molecules are trans to one another, although it's important to note that the formation of a cationic species in the middle is somewhat unique to iodine complexes compared to alternatives like fluorine complexes. However, upon heating, this moves to the final product of compound 2, where the phosphine ligands lie trans to each other. The mechanism with the trans isomer is very similar, with intermediate 4 being the same as intermediate 3, but with every group trans to one another. However, it is important to note that the final product is the same as the 1A mechanism. Now, let's consider the analytical methods used to study these reactions. This is predominantly different types of NMR spectroscopy. 13C NMR is used to identify the cis-trans isomerism in the phosphine ligands of complexes 3 and 4. The splitting patterns indicate that the phosphines are in cis in complex 3 and are in trans in complex 4. 195 platinum NMR is used to show the conversion between complexes 1A and 2, as the triplet peak in 1A is substantially lower than that in complex 2, as well as the conversion between complexes 1B and 4, as the triplet peak is slightly lower in complex 1B. However, it is important to note that platinum NMR spectra can vary wildly depending on ligand environment, so take these results with a grain of salt. Primarily, 31 phosphorus NMR is used to prove the formation and structure of complex 2. The complex 3 is a product of complex 1A when 1A is reacted with iodine at low temperatures, as you can see in this figure where the peaks of the 1A complex are much higher than that of complex 3, and also that the phosphine ligands are in trans with each other in complexes 2 and 4. Kinetic analysis of the spectra can also calculate the activation energy for the conversion of complex 3 into complex 2. This concludes my presentation on the oxidative addition of iodine to platinum 2 phosphine complexes. Thank you so much for watching.